everyone, welcome back. Today we're going to talk about the law of universal gravity. Now before we get into nitty-gritty or any problems, we need to have a conceptual discussion first. And since this is a first-year physics course, we're going to keep it as simple as possible. To start out with, any object with mass will create a distortion in space around it. That distortion will get weaker the farther away from that object you get. Now, any other object with mass that is in that distortion will feel a force from that distortion. That distortion is called a gravitational field. And like I just said, the farther away from the object you get, the weaker that gravitational field becomes. Anything in that gravitational field that has mass will feel a force in the direction of the field from the field itself. Let's give you a small visual. So let's say this is the Earth. Those arrows around it are a representation of the Earth's gravitational field. Now, this is the traditional way of drawing field lines. The closer the field lines are together, like here, the stronger the field is. The farther apart they are, like here, the weaker the field is. Now, for the AP exam, you may see something like this. The way they like to do it is what are called vector fields. The longer the vector in the field, the stronger the field is. And as I get farther from the planet, these vectors get smaller and smaller and smaller. So these field vectors get weaker and weaker and weaker. Now, let's say I have a spaceship. Here's my spaceship. Since the spaceship is in the Earth's gravitational field, the spaceship will feel a force, Fg. Let's say that force is 1,000 newtons. Since that spaceship also has mass, the spaceship itself also creates its own gravitational field. Since the Earth is in that ship's gravitational field, there is a force on the Earth that is also 1,000 newtons. In other words, these two objects are in each other's gravitational fields, so they exert a force on each other. They exert the same force on each other, which is a very important point. These are third law pairs. Technically, this is force planet on ship, and this is force ship on planet. These would actually be more appropriate designations here now, because they are third law pairs. And if one changes, the other one changes with it. One cannot exist without the other. So, if I take my ship and move my ship away from the planet, a few things would happen. Number one, let's say this force drops to 700 newtons. That means automatically this force would drop to 700 newtons because they are third law pairs. The ship is in the weaker part of Earth's gravitational field, and the Earth is in the weaker part of the ship's gravitational field because they are farther away from each other. So to sum up a bit, if you are standing on the planet, let's say the unit for weight you use in your country is pounds. If you weigh 150 pounds, the Earth is pulling on you with 150 pounds of force. That means you are also pulling on the Earth with 150 pounds of force. These forces must exist simultaneously. All right, let's start talking about relationships. And I'll use this space over here. So this force, Sir Isaac Newton actually discovered a relationship between physical properties and this force gravitational. And it looks something like this. Notice I'm not using the equal sign. If you were to double one of these masses, then this force would double. If you were to double either of these masses, this is mass 2, this force would double, which means m1, m2. Force gravitational is directly proportional to the masses. However, if this ship gets farther and farther away, this force decreases. This is a distance, but traditionally, since this formula is used a lot with planetary rotation, instead of a distance, they like to use radius. So we're going to use r for this because it is most commonly written this way, but keep in mind, this actually is a distance. They only use radius because this formula is used a lot in planetary motion. Now, the larger the radius gets, the smaller this force gets, so it belongs in the denominator. However, there's one more caveat, and that is this value is squared. So the farther these two things get away, this force drops off very quickly. If I was to do a representation of force gravitational in radius, it would look something like this. Now, if you notice, As r gets larger, force gravitational gets weaker and weaker and weaker. It gets weaker pretty quickly, actually. However, it never actually reaches zero. But at certain distances far away, the number is so small it might as well be zero. So let's take this relationship and work with it a little bit. So this shows the proportional reasoning relationship. If I was to double mass 1, force gravitation would double. If I was to double mass 2, force gravitation would double. If I was to double mass 1 and mass 2, force gravitation would quadruple. If I was to double radius, however, force gravitation would be 1/4 what it used to be. If I was to triple radius, it would be 1/9 what it used to be. Now, this equation is missing something, and that basically is a translator. In other words, let's say we have a 1 kilogram object and a 1 kilogram object, and they are 1 meter apart. If I do 1 kilogram times 1 kilogram divided by 1 kilogram squared, I would get 1. However, I would not get 1 Newton, because if that was true, everything in the universe would be crushed. Gravitational force is much weaker than that. So here's basically what the consensus was. We needed a value in order to translate this relationship to newtons, which means we need a translator in here. And that value is known as the universal gravitational constant. And here it is. So I'm going to make some changes here. This is now equals, I'm going to put G right here. Now let me show you real quick what this is and why it works. If I was to take this constant, G, 6.67 times 10 to the negative 11 Newton meter squared over kilogram squared, I'm going to multiply this by our 1 kilogram over 1 meter squared. What this value means is if I take 1 kilogram and 1 kilogram and put them 1 meter apart, these 2 kilograms cancel here. I get meters squared. That cancels here. I would get 6.67 times 10 to negative 11 newtons. So if I took a 1 kilogram object and a 1 kilogram object and separated their centers of mass by 1 meter, they would exert this much gravitational force on each other. Notice this value is very, 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 very small. You need a lot of mass to produce any substantial amount of force. That is why your weight is only its value, because you are near a very massive object, which is the entire planet. And notice how the units cancel out. So this is a fundamental property of our universe. If it was any larger, gravitational force would be stronger than it is now. If it was any weaker, gravitational force would be weaker than it is now. But long story short, this relationship finds you the gravitational force between any two objects, as long as you know their masses and the distance between their centers of mass. This value is a constant. It is on the AP exam equation sheet and it will not change. Okay, so now that we have this relationship, I'm going to put it down here in the corner, and I'm going to show you the 3 types of problems that you are most likely to encounter with this. Let's start with this first one. What is the gravitational force between an 80,000 kilogram truck and a 70,000 kilogram person who is standing 3 meters away from its center of mass? This is straight up using the relationship. Here's my relationship. Traditionally, it's written like this, but this algebraically is the same thing. 6.67 times 10 to the negative 11 Newton meters squared over kilogram squared, 80,000 kilograms, 70 kilograms, 3 meters, and this whole thing is squared, including the units. That means meters squared is going to be canceled, kilograms squared is going to be canceled here. I'm going to be left with newtons. I do the math, I end up with 4.15 times 10 to the negative 5 newtons. Now this is a massive truck, but this is a very tiny force. In fact, if I take this and convert it to pounds, I will get 9.33 times 10 to negative 6 pounds, which is pretty much a millionth of a pound. You wouldn't even feel this. So this is just using the relationship straight out. Side note, it is very common to be asked for the other variables, especially the radius. Rearrange the relationship would look like this. Okay, second type of question. 2 objects, A and B, exert a gravitational force on each other, F. If the mass of object A was doubled, the mass of object B was increased by 6 times, and the distance between the objects was tripled, by what ratio would the gravitational force on one of the objects change? So this is proportional reasoning. And I'm going to show you a technique here that works for pretty much anything. First, I'll put up my relationship. Now, it's important to note here, you are not finding force. You're not finding anything with a unit here. You are flat out looking for a ratio. So what I'm going to do is this. I'm going to do a little mathematical exercise called proportional reasoning. I'm going to do this twice. First, for every variable I have here, I'm going to put a 1. 1, 1, 1 squared. I do this and I get 1. Now notice I'm not even bothered with units here. Now, I'm going to do this again. And I'm going to change any variable that the problem has told me will change. In other words, g is a constant, so g is not changing. It's still exactly the same. The first mass is doubled. So this first mass is going to be a 2 now. It's twice my original value of 1. The other mass is increased by 6 times, so it is 6 times larger than 1. The distance between the objects is tripled, so the radius is 3 times, and this value is squared. I do this, I get 12 over 9, or 4 over 3, which could also be written as 1 1/3, or 1.33 repeating. So here's how this works. This value represents my original force value. This one represents what happens to it. So the answer to this question is, if F was the original force value, and I doubled one mass, made the other one 6 times larger, and tripled the distance, the new force would be 4/3 F. That is how the force value would change. It would increase by 133%. Just a side note, this type of question is very common on the AP exam for any topic, and this technique works very well for any topic. In fact, I actually didn't need this one because since g is a constant, it is definitely not going to change. But sometimes when I do that, it confuses people. So I literally could have done this only with the variables that actually had a possibility of changing, and it would have come out the exact same result. And once again, I'm looking for a ratio. This does not have a unit. Okay, so let's talk about the third common type of question with this topic. How much would a 70-kilogram person weigh on Mars? Now, I'm going to do this problem twice because there's something I want to show you. And we're going to make use of these. So we're going to do it on Earth and on Mars. This is the mass of the Earth, radius of the Earth, mass of Mars, and radius of Mars. So to start out, here is the Earth. Let's say you are standing right here on the Earth, and you want to use this relationship to find the gravitational force on you from the Earth. Well, you have the mass of the Earth right here. We're going to use this as the mass of the person, 70 kilograms, and the distance from center of mass to center of mass is approximately the radius of the Earth. So for this one, since I have my constant here, I'll just leave it as g. I'm just going to use variables here to save time. I'll call this mass of the person, mass of the Earth, times mass of the person, over radius of the Earth squared. For the sake of space, I'm not going to bother with the numbers this time. And if I do this, I get 688 newtons. Now, there's something I want to show you while I'm here. If I ask you to find your weight and you're standing on the Earth, force Earth on person, which this is in this case, would be mg, or mass of the person, times our gravitational constant, which was 70 kilograms times 9.81 newtons per kilogram. The AP exam uses 2 sig figs here, but in this case here, I'll use the traditional 3. I would get 687 newtons, which is almost dead on. So this relationship only works if you are standing on the surface of the Earth. While we're here, just to show you, a 687 Newton person is equivalent to 154 pounds. And you'll be finding both force Earth on person and force person on Earth. Okay, this means that using this relationship, we can know the weight of a person on any planet in the solar system if we know their mass and radius. So using this, we can literally find out how much someone would weigh on Mars, even though at the time of this recording, no human has ever been there. So the first one we did is force gravitational on the surface of Earth. I'll make this one the force gravitational on the surface of Mars. I'll put my little person here. It doesn't really matter where they are. The force is this way, and the force of the planet on them is this way. I do g, our constant, mass of Mars times mass of our person. Here's a mass of Mars right here, over the radius of Mars. This is squared, and I would get 260 newtons. And just to show you, that would be equivalent to 58.4 pounds. So a person that weighed 154 pounds on Earth would weigh 58.4 pounds on Mars. So long story short, the equation works the same way, and you would simply use the radius of the planet as your distance in this equation. All right, I think I'll end this one here. Have a good day. This is Mr. M signing off.